Look at the sheer physical footprint required to power heavy manufacturing. It takes a staggering amount of energy. This chart breaks down global energy consumption. When we map the energy transition, the focus is almost entirely on electricity, but thermal heat actually accounts for roughly half of all final energy consumed worldwide. Facilities processing food, beverages, and textiles require a continuous, highly stable supply of heat, ranging from 60 to 150 degrees Celsius. For decades, the industrial sector has operated on the assumption that only the combustion of fossil fuels, specifically natural gas and coal, possesses the reliable energy density to hit and hold that temperature range. You cannot simply bolt standard photovoltaic solar panels onto a factory roof and expect to replace a high-temperature industrial boiler. At this scale, single-point hardware swaps are insufficient. TIGI and their subsidiary, Solid, address this by replacing the entire thermal process, from initial generation to the final factory load. Removing fossil fuels from heavy industry is a multidisciplinary integration problem. It demands a coordinated overhaul in advanced thermodynamics, complex fluid mechanics, and the underlying financial model. The first engineering hurdle is the primary thermodynamic bottleneck of standard solar thermal generation in cold climates. When target temperatures exceed 60 degrees Celsius, standard flat or vacuum tube collectors lose the heat they just collected back into the freezing atmosphere through radiation and convection. This diagram illustrates TGI's physical solution, a patented transparent insulation known as the honeycomb collector. The precise geometry of this transparent layer allows incoming solar radiation to penetrate deep into the collector without obstruction. Once that light converts to heat, the honeycomb structure acts as a physical cage. It blocks conductive and convective heat from escaping back out into the cold air. Paired with a specific spectral absorption coating on the backplate, the design also eliminates radiative heat loss. The physics yield a precise result. Peak thermal efficiency is maintained between 60 and 95 degrees Celsius, even in the middle of a freezing European winter. But many industrial processes require heat up to 150 degrees. To bridge that gap, the architecture integrates advanced industrial heat pumps. These units operate at elevated pressures to take that 95-degree baseline and drive it up to the required 150 degrees. By stacking honeycomb thermal physics with high-temperature heat pumps, a facility generates high-grade industrial heat without burning a single cubic meter of natural gas. Generation is only half the equation. Peak solar radiation hits at solar noon, but factories run continuous operations, often hitting peak thermal demand in the dead of night. Storing thermal energy in water is a logical answer, but it introduces a fluid dynamics problem, internal mixing. Inside a massive industrial water storage tank, efficiency relies on perfect thermal stratification, maintaining distinct temperature layers. If the fluid dynamics fail and the water circulates, 90-degree water blends with 40-degree water. The result is a lukewarm mixture that immediately halts the factory's high-temperature processes. TIGI prevents this by engineering specific flow controls. Heated water is injected into the tank at the exact vertical height that matches its specific temperature, preventing disruptive turbulence. The system then extracts heat exclusively from the hottest, uppermost layer, ensuring the factory receives peak temperature output without interruption. This storage architecture scales far beyond single factories, forming the backbone of municipal district heating networks. Through their subsidiary Solid, TIGI applies these exact fluid dynamics across more than 200 large-scale thermal installations globally. At maximum scale, this enables seasonal thermal energy storage. Massive insulated underground reservoirs capture surplus solar heat during the peak summer months. That captured summer heat is effectively frozen in time. Months later, it is discharged to heat entire European cities during peak winter demand. Mastering thermal stratification transforms solar energy from an intermittent daily supplement into a reliable, continuous industrial utility. Hardware alone cannot react to fluctuating industrial loads or external market conditions. The architecture requires a central nervous system. This diagram maps the complete system architecture, centered around the cloud-based control unit connecting every physical component. This central hub constantly ingests data from the solar collector arrays, the industrial heat pumps, the stratified storage tanks, and the factory's live thermal load. Using that data, the cloud algorithm executes a continuous, real-time decision matrix without human intervention. It calculates the exact mathematical moment to spin up a heat pump versus drawing down reserves from the stratified storage tank. This logic is directly tied to the external electrical grid. The system tracks electricity tariffs, identifying the cheapest hours to overgenerate and store heat for later use. This cloud control layer provides real-time error detection and thermal load balancing, which minimizes both downtime and the total operational cost of the facility. The final and historically most restrictive barrier to adopting renewable infrastructure is the initial capital expenditure, or CapEx. This graph illustrates the traditional economic model of fossil fuels. Factories pay a relatively low initial cost for a gas boiler, but are locked into a volatile, rising operational cost curve. That curve is driven higher by carbon taxes, ESG mandates, and geopolitical supply volatility. Under the heat-as-a-service alternative, the capital required to build the solar thermal infrastructure is provided externally, dropping the initial cost to zero. The operational cost becomes a flat, predictable trajectory that sits immediately below the baseline cost of fossil fuels. This is made possible through strategic funding partnerships. Backed by global entities like the French corporation Aran, TIGI funds the hardware installation, integration, and maintenance. The factory no longer buys physical equipment or assumes technology risk. They sign a contract to purchase the clean heat generated by the system. Because the honeycomb physics and cloud optimization operate with high efficiency, TIGI can sell this heat profitably at a lower rate than what it costs the factory to burn gas. The heat-as-a-service model ensures that industrial decarbonization is a mathematically viable business decision on day one, separate from any environmental mandate. By combining honeycomb thermodynamics, stratified fluid storage, predictive cloud optimization, and zero CapEx financing, TIGI and Solid provide heavy industry with a definitive exit strategy from fossil fuels.